How does light reveal what the universe is made of? That's what we're going to talk about today. Hi, this is Jill from the Northwoods talking about nature right outside our front door. You know, my dad used to work in the Air Force. He was a military aircraft mechanic, worked on these gigantic planes, and there were different places where they could falter. But these are important pieces of equipment. They're not allowed to fail. We have to be able to fix it. And one of the things that my dad taught me when I was very young is that he would take oil samples from the engine, send it off to a lab. And this was just mind-blowing to me. When I was a kid, they'd look at the oil, just the oil, and from looking at the oil, they could tell what is happening deep inside this engine, even though they couldn't open it up in that same way. If a certain metal showed up in the sample, it would tell them which part was wearing, which part was wearing down, and then the bits of those metals were falling into the oil. Was it the pistons? Was it the crankshaft? Was it just nuts and bolts? Was it this or that? And when I was a kid, this just absolutely blew my mind. And you're wondering, what does this have to do with nature outside our front door? Well, I'm going to tell you that next. This technique is called spectrometry. And the more I've learned about it, the more I think it's one of the quietly most extraordinary tools we have in science. And it's probably something you never heard about. But my dad used it, like I said, to diagnose broken machineries. This same idea is what astronomers use to figure out what planets on the other side of the solar system are made of, without ever going to the other side of the solar system. And that's what we're going to do. We're going to do a small series about spectrometry, how we use it in nature. And we're beginning, at the beginning of the science of this. And once you understand the principles behind it, I think it's going to blow your mind. So first of all, what is spectrometry? So we're not going to do a deep dive. We're not going to, blow everyone's mind. But the idea is this, is that when you see what looks like white light, right? A lamp, sun, I got a yellow light there behind me. When you're looking at it, what you're actually seeing is a mixture of different wavelengths of light all traveling together. And those wavelengths are how we perceive a color. And when you see the wavelengths, if you've ever looked like at a rainbow or sunlight that hits a prism, prisms are like the pyramid-shaped items, the light spreads out into spectrums, red, orange, yellow, green, blue, violet, right? Just like the rainbow. Because each of those wavelengths bend slightly differently. The rainbow you see isn't just pretty, it's information. The idea is that everything, every element, every substance interacts with light in its own unique way. And so when atoms are heated or energized, like I said, this is a little deep dive, their electrons absorb energy. And they jump to higher levels of energy and then they fall back down again. And you can kind of see how it goes, is that you get these excited particles of energy, you get energy as light, and then you get energy as heat. Heat kind of goes down in that line. But it's a fingerprint. Each element has its own different kind of production of visible light. Sodium produces a very distinctive bright yellow light. Copper produces blue-green light. Potassium produces pale violet, so on. Spectrometry, it takes an instrument, it's a spectrometer, that takes the wavelength, spreads it out, and looks at the component wavelengths that are there, measures exactly which wavelengths are present in which amounts. And then the scientists can use this particular pattern of lines so they know exactly what elements were involved in this process. I mean, that's the whole idea right there. So like I said, not a deep dive in science, but essentially by looking at that particular kind of light, we can kind of see it. So this is kind of an easy way for you to think about it. Chemists use a very simple version of this called the flame test. This was one of my favorite things that we did in chemistry when I was in high school. So you imagine that if you have a little flame on a candle and you sprinkle maybe like ordinary table salt into the flame, the kitchen salt, sodium chloride, right? It immediately turns a vivid electric yellow. The yellow is specifically from the sodium atoms that when they got heated up, they energize, and their electrons release this wavelength of a particular yellow. The sodium's fingerprints is distinctive, and it's easy for us to spot. But if we had some sort of a copper compound, copper salt? I don't know. If we had some sort of a copper compound, and like I said, you sprinkled it in, you get blue-green. Potassium would give you pale yellow. Lithium would give you a deep crimson red. And each element has its own signature, and the flame is what makes it visible. So here's the fun part. My friend and I go camping every year, and I buy these packets of I just looked at the chat like she's watching me say this. But I buy these little chemical packets, and what you do is you throw them into the campfire, and the flames turn blue and purple and red, and packs cost $1. And what they actually are is they're metal salts. So you will get copper chloride, blue-green, strontium, which is red, potassium for purple, and the fire heats them. Each of these metals release a light color characteristic to its own wavelength, and those color mixings you see are those salt metals burning in the flames together. And so your eyes are sort of doing a rough version of what a spectrometer does. By reading in those colored light sensations, you can see multiple things are present at once. So the spectrometer, what it does is it actually does it with just better precision. It breaks the lights into exact wavelengths, identifies each element that's present. And so if you've probably seen this same kind of principle without even knowing that you've seen it. So think about the orange-yellow street lights. You know, those older cities that had the older street lights, that's because they had sodium vapor lamps. They were warmer light, and it turned that light that was coming out of the street lights this kind of flame yellow orange in it, and those lit the entire streets. Now we have different kinds of lights that are almost like a very blue-white light to them. But that's the idea. So if we go on and talk about this even further, one of the big applications we did, this was a remarkable moment in history. In 1868, an astronomer was studying light from the sun. And during a solar eclipse, they ran the sunlight through a spectrometer and carefully mapped the lines that came out of it. And then we were able to see exactly what was in the sun's outer atmosphere. The lines matched known elements. And it wasn't just one line, a yellow line that didn't correspond to any element that we had seen on Earth or ever been identified. Nowadays, we know this element to be helium. We named it Helios for the sun. But for 27 years, helium was known as an element that was only found on a sun 93 million miles away. In 1895, a Scottish chemist named William Ramsay was experimenting with uranium minerals here right on Earth and found a gas was being released in that same spectral line. It had the same fingerprint. Helium had been here all along. We just didn't know how to find it. And so when I think about that story, that scientists were able to discover and identify elements that they'd never touched before, never seen before, never detected before on this planet, purely by reading the light from the sun. The fingerprint was there. It was clear as everything, just waiting for someone to notice that it was there. That's what spectrometry actually is. It's reading light waves in a way a detective reads evidence. So now let's bring it back to my dad and his engine story. When those technicians that were on my dad's team ran the oil through the spectrographic analysis, the engine runs these tiny medical particles inside, wear off, and get suspended in the oil. They're almost invisible to us, but the spectrometer can read them and detect them. So iron particles point towards the cylinder walls or the gears. Copper points towards the bearings. Aluminum points towards the pistons. Chromium has points toward the piston rings, and each metal leaves a trace amount of essentially a part of that engine, and it's raising its hand saying, I'm being worn off. I'm actually what's going into the engine oil. By using this on the aircraft engine, these heavy industrial pieces of equipment, military equipment, Any failure in those equipments would be catastrophic. But the oil tells a story about what the breakdown is happening. And you might even think about the forensic labs using spectrometry to investigate paint chips, glass fragments, gunshot residue, fibers, tiny samples that are almost invisible to the naked eye can detect and reveal certain types of chemical compositions. Analysts can then use that to piece evidence together that maybe something came from the same source. The same evidence maybe would be found at two different locations was the same thing. Or when hospitals use mass spectrometry to analyze blood, tissue samples with extraordinary sensitivity, doctors can detect drug in concentration, trace metals like lead and mercury that can cause metabolic abnormalities, vitamin deficiency. Mass spectrometry is so precise that it can identify substances at parts per billions inside of our own drops of blood. I remember hearing this story about someone, she looked and was acting, her body was acting like she was diabetic, but she was not having high glucose problems. Doctor was just like perplexed. Why is this person acting like they have diabetes and they don't? He ended up running her blood sample through and found out that she was being poisoned through heavy metal. And once he was able to get her out of whatever situation was causing the heavy metal problem, and then using systems to help clean out her blood, she ended up getting better. She actually was not diabetic at all. So this is really miraculous. But basically, being able to find this kind of precision is essentially like looking at a single drop of something in an Olympic-sized swimming pool. That's what makes this so remarkable. Scientists also use this for certain kinds of environmental monitoring methane, nitrogen, carbon monoxide, ozone in our atmosphere. The satellites are equipped so that they're able to have spectrometers that measure certain types of gases from various kinds of pollutions, giving researchers this idea of, maybe one particular factory is producing one kind of pollution. How is that moving over the earth? How is it changing over time? Food safety. Spectrometer is used to test food contamination, pesticide residue, some kind of ingredient that shouldn't be in the food, and it can detect whether the olive oil has been diluted with a cheaper oil, or whether the honey has been cut with corn syrup, or whether the food produced is actually what's in the food that's being claimed. These fingerprints cannot lie, and so it can tell us the truth of certain kinds of situations. But what's going to be exciting about is we're going to talk about this the next time, is we're going to talk about how this particular information is used not just for blood work and atmospheric data, but how the elements leave its fingerprints in light and how we can look at lights. We don't have to go and get samples from stars and planets. We don't have to send a space probe out so that we know exactly what something is made of. We're able to look at the light and figure out the composition of certain pieces of the atmosphere, the planets themselves. And that's what we're going to talk about next time. This is an exciting kind of science. So hopefully this kind of gives you a moment. Spectrometry is not just science outside your front door or in your campfire or in blood analysis or atmosphere analysis. This is something that is underneath a bunch of different science. There is a fundamental understanding that when we are able to reveal secrets through just light itself, and we learn how to read light itself, you'll be able to know exactly what's going on there. And when my dad and his colleagues were able to figure out what was inside of that oil, they were able to fix the plane. So the end of it, when my dad and his coworkers were able to get these lab reports back, they could figure out what was making a plane not work correctly and fix it. When we look at fireworks and we look at the blues and the reds, we understand why that's happening. Every astronomer who's ever pointed a spectrometer at a star is doing exactly the same thing as those early chemists were doing in their flame tests. It's just on a much more accurate scale. The next time, like I said, we're going to talk about the planets and why planets are certain colors. I hope to see you then. Remember, this is Jill from the Northwoods. You can find everything I do at jillfromthenorthwoods.com. You can contact me. If there's something that you saw about color and light that interested you, I'd love to hear from you. Thanks so much. Have a great day.